Hi everyone, and welcome back to the RMETS Virtual Student and Early Careers Scientist Conference 2020. And thank you for joining us for the second day of the conference for Session 6, Climate and Environmental Change. I'm your chair, Joanna Raymond, a PhD student in Environmental Sciences at the University of East Anglia. And we have a very diverse set of presentations for you today, so it should be a great session. I'll be introducing each of our 5 oral presenters, and they will have 10 minutes each to present, followed by 5 minutes of questions. As with yesterday, only the presenters will have access to their microphones and webcams. So if you do have a question, please just send it in the chat, and I'll try and ask as many of them as possible in the Q&A after the presentation. So first up today, we have Alice Ramsden. So Alice, when you're ready, you can start your presentation.
Hi everyone, I'm Alice Ramsden from the University of Bristol, and today I'm going to be talking about my project on quantifying methane fluxes from multiple sources using observations of co-emitted gases. So this plot here shows the global budget of methane emissions averaged for 2012, and methane has a range of natural and anthropogenic sources, as you can see here. It's a very strong greenhouse gas, so it's important that we can understand these sources well. My project is focusing on the fossil fuel methane emissions, shown here that's about 20% of the total. It's important that we can understand these sources, as atmospheric concentrations of methane have been rising rapidly since the Industrial Revolution, particularly in the last few years, as this plot shows. This plot shows the global methane concentrations from about 1980s till now. And this rapid rise recently is not particularly understood in the literature. So we need better models and an improved understanding of methane in order to solve this issue. There are multiple ways of studying atmospheric methane. One of them is using inventory data. So this is where bottom-up, it's called bottom-up methods. These where methane emissions are modelled, emissions from the surface are modelled. So for example, if you wanted to look at how much methane is emitted from cows in the UK, you'd multiply the number of cows by the amount each cow emits. This is a very simplified model, but more complex models can be used to produce maps like this one on the left, which shows the spatial distribution of methane emissions in the UK. Another way to study methane emissions is to use atmospheric observations. You can then use these observations to infer surface fluxes. So for example, you can use satellite data like the plot in the middle, or ground station data, which make observations at single sites, such as the image on the right-hand side from Macehead in Ireland. My method uses both types of data. So I infer emissions from the surface using atmospheric observations, but I also use this inventory data as a prior estimate of these emissions. So in order to compare these two data sets, as they're obviously quite different, the inventory data is a spatial map, whereas the observations are often taken at one point in time one spatial point over a long period of time. So I have to use the Met Office's numerical atmospheric modelling environment transport model, which models the movement of particles in the air. Sorry, my slides are skipping around a lot. Which models the movement of particles in the air from their detection point in the atmosphere back to where they're emitted from on the surface. So by combining all these 3 points of data and comparing the probabilities of the inventory data against the atmospheric observations, I can end up with a posterior estimate or an improved estimate of these surface emissions. But as these observations can't attribute emissions to their source just on their own, we have to rely on the inventory data, the spatial distribution of emissions, to tell us where the source of these emissions. This is the traditional way of doing things in assigning emissions using inverse models. I've got a couple of examples here. The top plot shows anthropogenic methane emissions, so from fossil fuels or fossil fuel use and distribution. And the bottom plot shows methane emissions from wetland emissions, which is the largest natural source. However, these models can be often be quite inaccurate, as they rely on taking averages over large areas, or can use out-of-date information. So this isn't always reliable. So another method for attributing methane emissions to their source is to use measurements of the isotope ratio within these emissions. So different sources of methane have different ratios of heavy and light isotopes. But again, there was problems with this, as these characteristic ratios can overlap and not very well understood. As this plot shows, this is a plot of the characteristic isotope ratio for a range of different sources. And you can see the distributions of these overlaps. So if you wrongly assign, use an incorrect ratio, you can often wrongly assign these emissions to their source. So I'm using a different method, which involves using observations of a secondary trace gas that is characteristic of only certain sources of methane. So I'm currently testing this method using observations of ethane, which is emitted from fossil fuel sources of methane, like oil wells, in the coal mines, and in the production and transportation of these fuels. But there is no methane, there is no ethane emitted from methane's other large sources, such as agriculture and wetlands. So if I measure a characteristic ratio of methane and ethane in the atmosphere, I can then infer that these methane sources are from a fossil fuel source. So I'm using this new methane emission method along with an inverse model. So I've had to adapt the standard single gas inverse model framework to incorporate these new observations. So I'm currently doing a pseudo data test of this method over the UK, where we have access to lots of data. So instead of using a single inventory prior, I have to split this up into sectors and also provide a prior for the ethane observations. I then can use ethane and methane observations from tool tower sites around the UK, along with the atmospheric transport footprints, which can apply to both gases. So I'm just going to go through a couple of my pseudo data test results, which answer a couple of questions which are important when testing this method. So I'm going to look into how does adding these ethane observations and the emissions ratio between ethane and methane affect the posterior emission uncertainties, so the uncertainty we have on the estimates of methane emissions. And also I want to understand how wrong this ratio between methane and ethane can be before the results are actually worse than a single gas case. So this plot here shows results from 6 different test runs of this model compared to the prior information. So this is the posterior mean and standard deviation of the 6 tests on the right against the posterior mean and the standard deviation of the results on the left. So the coloured dot shows the mean emissions, and the error bars and the annotated values show the standard deviation. So I did one single gas test, which is in the second dot, which showed in light blue, which shows some improvement towards the true emissions ratio, the true emissions that I'm trying to replicate in this model, which is given by the grey dotted line. It shows some improvement based on the prior, but the 2 gas tests, which are the 5 values on the right, all show an even greater improvement. So these 5 tests are all slightly different because I assigned a uncertainty to the prior estimate of the ratio. And this increases from 0.1 to 0.5 from left to right. And you can see it as the uncertainty on this ratio increased, the posterior estimate started to move back towards the single gas case, which is what we expect. So if we we have little understanding of this ratio, it's equivalent to having a single gas case. But there are some values at which, some uncertainty values of the ratio at which the results show a big improvement to the single gas case. This plot can also show, give an answer to my second question of how wrong this ratio can be. As in the first single gas test, sorry, the first two gas test, I gave a very low uncertainty to this prior ratio, which was slightly incorrectly specified to see if the model could retrieve the correct value. And you can see here, when there was a low uncertainty on this ratio, the posterior mean of the emissions is skewed far beyond the prior and single gas cases, which shows that I need to be careful when assigning this ratio, as it could possibly make my results even worse, which is an important thing to consider when testing this method in the future. So as I said, I'm doing a pseudo data test in the UK, and then I'm going to do some full real data tests to assign emissions based on their location. And I'm hopefully going to use this method to study US methane fossil fuel emissions, as there's discrepancies in the literature over the magnitude of the trends in these emissions at the moment. And then hopefully this method I'm going to adapt to use with different gases for different sources of methane, as it should be highly adaptable. Thank you for listening. I'm happy to take any questions you have.
Thank you so much, Alex. So now we'll ask some questions. So we've got a few already in the chat. We've got one from Liz who says, how big is the contribution of methane from ocean seabed, and do you factor this in to the contribution? Do you factor in this contribution?
That's a really good question. I don't currently look at that because I'm very focused on anthropogenic methane emissions. I mean, one of my colleagues does she looks at freshwater methane, so not ocean emissions. But this, it can be quite a large source, but I'm not sure, it's not what my project's focused on.
Okay, and another question, are there any ethane sources that aren't linked to methane that could affect your results?
There's a chance, well, there's some information in the literature which suggests that there's some emissions from agriculture, so from manure management and livestock, there could be very small emissions, which I certainly will need to consider, but it's likely to be small enough that it shouldn't have an effect on my results. Okay,
and I've got a question for you. Is there a sort of a similar gas or that can be used as a tracer for agricultural sources? Can you do something similar?
I've been thinking about that recently. It could be that you, because there's lots of nitrogen used in fertilizers and lots of aspects of agriculture, so it's a possibility. But there are also emissions of sort of nitrogen oxides from car fumes and things like that. So it's a possibility, but it could be difficult, which is why I'm just testing this method using ethane for fossil fuels. It's a very specific test case.
Okay, and I think the last question, do you use set values for emissions? Sorry, I can't read this very easily. Emission types, or vary them based on region, e.g. certain gas source may have different ethane-methane ratios? That's a good question.
That's a really good question, because there's a lot of, there's some papers recently have shown that this ethane to methane ratio can vary, as you say, spatially, but also over time. For example, oil pipelines can use different ratios of ethane depending on what's economically viable at the time. And for example, coal mines have particularly high ethane to methane ratio compared to natural gas. So it's likely this will be something I'll definitely have to take into account. And my model is quite adaptable. So I, using this emission ratio, considering it at the same spatial and time scales as I'm solving for emissions themselves. So I should be able to factor this in quite easily.
Great. Thank you so much, Alice. So I think now we'll move on to our next presentation, which is from Brooke Snoll. So Brooke, if you want to get your webcam on and if you're ready to present.
Hi. Okay. Hi, I'm Brooke, and I'm an MRes student at the University of Leeds, and I'll be talking about abrupt climate change that occurs in model simulations and determining what could have caused it. So I'll be going through what is happening first. So just to describe what abrupt climate changes mean when discussing paleo or longer time scales, talking about abrupt cooling or warming within centuries or decades. And so I've been looking at multiple simulations of the last deglaciation using the Hadley Center General Circulation Model. These simulations follow the PMIP4 protocol for comparing different model simulations for these time periods. And I've originally taken a grid box around Greenland surface air temperature. Seemed like a good place to start in Greenland because there's a lot of proxy records for this time period just to compare. And seeing an abrupt climate change that occurs that I've highlighted here at about 15,500 years ago. You can see there's also one at about 1,000 years later, but just for time's sake, I'll be focused on the first one, but if you have any questions about the second one, I'd be happy to answer. So just looking at what could have caused this, this will not only help with understanding abrupt climate change more, but also how to reproduce them in model simulations. So as I mentioned, this is occurring in the last deglaciation, which began around 19,000 years ago, or at the end of the last ice age. You can see from the middle figure that at the last ice age, ice sheets were much more widespread across North America and Eurasia. Since then, there's been extensive global warming, ice sheet reduction to the present day ice sheets, sea level rise, increases in atmospheric greenhouse gases, and increases in insulation. And you can see this in the figure on the right. And all of these are the realistic boundary conditions that are going into the model simulations. Also, something to note that during this time period, there are multiple abrupt climate changes seen in proxy records. And these are normally attributed to changes in ocean circulation. So where is it happening? So this figure on the top right is just a zoom in of the 15,500 year ago event from the first slide. You can maybe more clearly now see that there is a cooling within a few centuries and warming even faster within decades. It's about a 2-degree decrease in temperature as well. So I wanted to further investigate the seasonality and the magnitude of the cooling and the warming. So from now on, I will focus on the winter signals because that was the largest signal for surface air temperature. And then as far as the magnitude goes, I've taken 10-year means at before cooling for the orange line, peak cooling, the yellow line, and the green line at peak warming, and then calculated anomalies between these to get the magnitude. So the color map in the bottom left is the cooling signal. And you can see that originally I was focused on Greenland, but a majority of the cooling seems to actually be occurring around Northern Europe and the Nordic Seas, or like Fennoscandia. And for the warming signal, kind of the opposite, but again, like strong signal around Northern Europe and Fennoscandia. So Wanted to then look at a time series over Fennoscandia just to compare, and we're seeing an even more abrupt cooling and warming, and the cooling period also seems to last longer. This is also about a 3-degree decrease in temperature, opposed to only about a 2-degree. Also, something to know is there is a kind of a dipole pattern you may be able to see, where there's like warming in the Labrador Sea and cooling in Fennoscandia. I'll touch on this later. So why is it happening? So as I mentioned before, a lot of the abrupt climate changes during this time period are attributed to changes in ocean circulation. So naturally, that was the first thing that I wanted to check. However, I've checked multiple simulations, some with even different freshwater forcings, and this climate change is occurring in every single one of them at the exact same time. And not only this, it's occurring with or without an ocean circulation response. So it seems like it's not dependent on the ocean, and it could instead be something to do with the atmosphere. So as I mentioned, this dipole pattern where there's warming around like Eastern Canada and cooling around Northern Europe, and it kind of resembles the North Atlantic oscillation. So just as a brief overview, the North Atlantic oscillation is a weather phenomenon that's highly dependent on the shape of the jet stream, as you can see on the left figure. And then in the right figure, as you can see, it creates this quadruple pattern across the North Atlantic with opposing conditions in Fennoscandia and the Labrador Sea area, which is what I was seeing in the color maps. And the northern annular mode, in contrast, is a pretty similar concept, but normally describes more hemisphere-wide changes opposed to just concentrated around the North Atlantic. So in order to calculate the indices for these phenomena, in order to learn more about how they are interacting with the surface air temperature, I have to look at atmospheric pressure at sea level. So these are the same anomalies as before with the winter cooling signal and the winter warming signal. And you can see for the cooling signal, there are high increases in sea level pressure hemisphere-wide, and in a lot of the same places where we are seeing the cooling as well. And the warming signal, again, kind of just the opposite, but high decreases in sea level pressure hemisphere-wide. So to investigate this further, I've looked at seasonal northern annular mode indices, and I've chosen northern annular mode opposed to the North Atlantic oscillation just because we're seeing those hemisphere-wide changes in pressure opposed to just around the North Atlantic. And so these are zonally averaged meridional pressure gradients between 65 degrees north and 35 degrees north. And you can see there, if you focus on the winter time, so this the blue one, you can see that there are, it's a very abrupt decrease and increase similar to the surface air temperature. And again, it was a winter signal we are seeing in the surface air temperature as well. So here's just the two on top of each other. And you can see that they're almost the exact same shape. The magnitude is a little different, but almost the same pattern. And to investigate this further, just decided to do a linear regression. So I've regressed surface air temperature onto the northern annular mode. You can see on the bottom left, I have the winter R² values, and the numbers are a bit difficult to see, but we're seeing relatively large correlations in locations where surface air temperature was changing the most. So in Northern Europe, Eastern Canada, and Greenland. And if we look at the slopes, we can see that there's a positive correlation around Fennoscandia, which means so as northern annular mode is decreasing, surface air temperature is decreasing, which again is, you can see not only from the time series in the upper right corner, but we also saw that in the color maps. And for around the Labrador Sea, we're seeing that there's a negative correlation. So we're seeing as northern annular mode is decreasing, surface air temperature is increasing, which again, we saw that in the color maps. And not only this, we're seeing about a 1-to-1 ratio. So it is explaining, so the northern annular mode shift is explaining all of the surface air temperature shift. However, it's not exactly explaining what is triggering the northern annular mode shift. From here, a lot of my results are a bit preliminary, so I don't have figures on it, but we're seeing, we know that changes in the ice sheet heights can affect the jet stream. And so we're seeing a lot of changes that follow a similar pattern in North America around this time, and we're thinking that it could have to do with each other. So just to wrap it up, I've been looking at both of these abrupt climate changes of about 2 to 3 degrees in the model simulations. Just to bring it back to the second event, seeing very similar changes for that event as well, the northern annular mode change, and thinking that it could be triggered by ice sheet melt in North America around this time. Thank you.
So now we've got time for a few questions. So we've got a question from Arthur. He says, what is the spin up of these simulations, i.e. do you give them enough time for the ocean circulation to adapt to ice sheet forcing, and for example, for the AMOC to change or collapse?
Yeah, they definitely have enough time. These simulations were, they were, it's been run since 23,000 years ago, but they also are individual 500-year simulations that have been pieced together, or actually they're 550-year simulations. And 50 of those years are used as a check to make sure that everything is working as it's supposed to. So, yeah.
Great, thank you. So if anyone has any other questions, just type them in the chat. So this is mostly, you're using model data, right? Do you sort of check it against any observations, or is it driven by observation model?
I mean, the boundary conditions have been driven by observations, but the actual model output does not necessarily correlate with proxy records or with surface air temperature as it's been inferred from proxy records. However, it does still give insight onto how abrupt climate changes work in the real world. So, yeah, but it's not. This is not an event that has actually happened within proxy records, but it could help explain one that has.
Makes sense. Oh, and we've got one more question. Arthur again, thank you. So do you know if the HAD-CM3 model does well in simulating the NAM in modern day?
I know that they have used the HAD-CM3 with NAO more specifically, and it does seem to create the expected pattern, but it is something I have to look into more to make sure that it would be showing the correct pattern, but it does seem to be from, at least with the NAO.
Presentation and answers.
Thank you.
Hello everyone, I'm Xinyue, currently a first-year PhD student at the University of Leeds. I'm very glad to introduce my research work here. The topic is increasing global mountain forest loss in the 21st century. First, talk about the background. It is well accepted that mountain forests play a very important role in many aspects. For example, mountains often function as water towers, so mountain forests are of significant hydrological importance. Also, they are usually biodiversity hotspots, especially for endemic and threatened species. What's more, because mountain forests grow at higher elevations or steep slopes, they tend to be more vulnerable to climate change. Therefore, they can be indicators of climate change and in turn have a potential role in combating climate change. However, mountain forests have experienced great change and are currently under threat. These changes have great impacts on climate through a variety of processes. For example, they may change regional rainfall patterns and may have warming or cooling effects to the regional environment. Therefore, mountain forest cover change needs particular attention. Recently, more and more studies have paid attention to mountain forest cover change. For example, in the mountainous province of Thailand, there is an overall increasing trend in annual forest loss, and the forest loss has moved to steeper land at higher elevations, especially since 2012. Further, in the whole Southeast Asia, deforestation has shifted from the lowlands to the highlands. However, highland deforestation in land use data sets used in many climate models is usually automated. There is often poor representation of mountain topography in coarse resolution or system models. Also, in East Africa, most deforestation was found in the lower and middle elevations of the mountains, and the mountain habitat zone has more endemic species compared to the other zones. But previous work is limited at a regional scale. We know our Earth is a highly related system, so we need global research on mountain forest cover change. In this case, these studies motivated us to explore how forest loss is distributed across global mountains, as well as the implications for biodiversity hotspots. In this study, we first used high-resolution satellite-derived forest loss in each year to explore the spatial temporal variations of forest loss in the mountains during 2001 and 2018. Then we investigated the change in the elevations of mountain regions where forest loss occurred in the year by combining the high-resolution elevation dataset. And last, we assessed the biodiversity loss due to the mountain forest loss in the period via the biodiversity hotspot map. We used 4 types of datasets in this study, including Hansen's forest cover change data, elevation data from AST Global DEM, GMBA mountain definition, and IUCN's resulting maps for spatial richness and range sensoriality. Now let's move on the results. We first look at the time series of annual mountain forest loss during 2001 and 2018. The result shows annual forest loss in mountains has increased by more than 3 times during 2001 and 2016, but decreased in 2017 and 2018. The right figure tells us the mountain forest loss has occurred at which elevations in each year. It shows forest loss has not been even across all elevations. It has been the greatest in the lower elevation of mountains, meaning below 1,200 meters. Then look at the spatial patterns. In the above 2 figures, areas with larger forest loss and high loss rate are in red. So we can know mountain forest loss is increasing not only in the tropics, but also in many places at middle and higher latitudes. To be specific, Southeast Asia, Siberia, and Canada have experienced a large area of loss with a high loss rate. As for the elevation of forest loss, Green in the below figure means a decreasing trend in average elevation of forest loss. So we are glad to see forest loss has moved downwards in South America and southern China, partly due to some positive policies in forest recovery. However, there are still many mountains where forest loss is climbing up and to higher elevations, which is shown in red. Next, we try to find the elevational gradients of mountain forest loss. Relative mountain forest loss was calculated as the proportion of annual forest loss to the forest area in the base year. It shows the elevation of the largest percentage forest loss went upwards in earliest years, but moved downwards recently. From the right figure, we can see the number of forest loss pixels in 2018 surpasses the numbers in 2001 in all elevation bands, but the average elevation of loss has slightly declined. Last, we focused on biodiversity. Biodiversity hotspots were identified based on species richness in green and range size rarity in red, only for threatened species here. We find substantial losses showed in red are located in mountain forests of Andes, Himalayas, and maritime Southeast Asia. Our results also indicate there is an increasing trend in annual forest loss within biodiversity hotspots in mountain regions. Around 38% of mountain forest loss is in the biodiversity hotspots, and relative forest loss within these hotspots is much higher than other mountain regions. So, in summary, we find annual mountain forest loss has tripled in the 21st century, and as mountains are physical barriers to human exploitation, substantial losses in forest cover are concentrated in the lower elevations of mountains. The third point is the average elevation of mountain forest loss at a global level has moved downwards recently, which is different from the regional study on like Southeast Asia because policies on forest recovery protect trees from logging in sensitive mountainous areas. And the last is many mountain forest loss regions are also biodiversity hotspots. Forest loss in these mountainous biodiversity hotspots has significantly increased. So this is our initial study on mountain forests. In addition, forests can affect water and climate through a variety of mechanisms, such as evapotranspiration and atmospheric moisture transport. So forest cover change patterns can have large hydrological effects. For example, mountain forest loss can impact regional rainfall. So my PhD study will further look at the impact of these mountain forest cover changes on the hydrological cycle. Thanks for your attention. If you are interested in my work or have any questions, please do not hesitate to email me.
Xinyue, I think if you want to join us on webcam for questions.
Sure.
Great, thank you. So if anyone wants to ask a question, if you put it in the chat. So do you think you'll look at the effect of the relative forest loss in the biodiversity hotspots? Are you going to look at the effect that that has on biodiversity? Or is that sort of outside your project?
Sorry.
Are you going to look at the effect of the forest loss in those biodiversity hotspots? Will you look at how it's affecting biodiversity?
Yeah, actually, currently I just calculated the first loss in the biodiversity hotspots. Yeah, but yeah, actually, I do want to know the biodiversity loss due to the forest cover loss, but I don't have a well background on biodiversity, so maybe I should read more literatures to look at the biodiversity loss. Yeah, it's a very good question. Yeah.
I imagine that would be an entire PhD project in itself. So, yeah.
Yeah, sure.
Got a question from Viola. She says, can you quickly explain further how to plan to investigate the impact of forest cover change on the hydrological cycle? So what are you going to do for that?
Yeah. Thanks for your question. Yeah, because forest cover change have a important effect on evapotranspiration and rainfall and precipitation and lot of things in the water cycle. So but I think I cannot focus on everything in the water cycle. So I just focus on one or two things of the water cycle, such as the rainfall, such as the rainfall patterns, at a regional scale. Maybe I will choose a case study to look at that.
Yeah. That sounds sensible. If anyone else has any questions. And I was just also wondering, there was a graph where there was the annual forest loss. And I think there was a very big peak in, was it 2016?
Yes.
And then it started to decrease again. I'm assuming that's because policies have been introduced. What caused the big peak and then the loss?
Yeah. I have noticed that, and I plot anomaly maps for the forest loss in that year, and I find it's higher forest loss in Canada and Russia. I thought that would be some big fires, to cause that. And other reasons would be the continuous exploitation, such as in some developing countries, like Southeast Asia. So these two main causes truly the peak in 2016.
That makes sense.
Yeah.
Thank you.
Thank you.
I think that's all from the questions. So thank you for your presentation again. So now we'll move on to our final speaker of this session. So Sarah Greenham, if you want to join us for your presentation, that would be great.
Hiya, thank you. So, hi everyone, my name's Sarah. I'm a second year PhD student at the University of Birmingham in civil engineering. My PhD project is on the climate change and heat related impacts to the London Underground infrastructure. So to give a background about the London Underground, it's the oldest subway network in the world. It comprises of 402 kilometres of track across 11 lines and about 270 stations. The development of the first line, the Metropolitan line, led to the rapid suburbanisation of the northwest of London around the boroughs of Harrow and Hillingdon in particular. So my research aims to identify the trends and characteristics of heat-related asset failures across the network. So that's not necessarily looking at people passing out or falling ill on trains. So I am looking at some of the sort of highlights of the project are to look at, are there any hotspots, any geographic hotspots, any problematic areas on the network? What type of assets disproportionately affect the the network and cause delays? And are there any seasonal trends, annual trends, and diurnal variances? And can we add climate projections to this to identify the future risk? The talk I'm going to give is a little bit about a particular part of the work I've been looking at on predicting tunnel temperatures. Following some research, I went out to Tokyo to the Railway Research Institute, where they helped me with some modelling of tunnel temperatures using air temperature. So a little bit of the motivation of my research is that because of the age of the infrastructure of the London Underground, it was not built to accommodate the current capacity. Because of the rapid growth of the city above, it's led to poor ventilation underground, which is now hard to retrofit with cooling mechanisms. The London Underground, according to Transport for London, TfL, find heat risk is the greatest compared to any other transport modes that they have, and this is due to the tunnels. What's happened is that in the last century, the temperature has grown, is doubled from 15 degrees to now on average 30 degrees. This doesn't mean that it's the same across all the lines, because the lines were all built at slightly different times and they all operate slightly differently. What it's led to is some differences in the trends and the patterns of each individual tube network. So on the left here is the 12-month rolling average of the tunnel temperature for each line that has a deep tube network from 2013 to 2017. And you can see that the overall trends on each line are rising, especially the northern line over some recent years. But the northern line is the black one. The brown line is the Bakerloo line, and the red is the central line. And these are particularly warm and also showing signs of increase. The Victoria line in the cyan blue in the middle, you can see has also been recently increasing. Similarly, the types of delays that take place vary over time, depending on the asset. So on the right here is a graph of some of the different asset types and the types of measured delays that take place owed to those types of infrastructure. So you can see that the fleet, which is the rolling stock, or the trains themselves, faults due to them are quite variable and have a greater share of proportion of delays over time, as opposed to signalling, station and track related failures, which are also quite considerable, but over time have shown some sign of decline. So there is a knowledge gap on linking this relationship to tunnel temperature to these types of asset related delays. So in my master's, I also did look at this at quite an aggregated level, and I recently published this research. It was published last week in Meteorological Applications Journal. This is one of the graphs taken from it. You can see that the data is from 2011 to 2016. I have taken the mean daily maximum temperature recorded at weather stations via the Met Office and mapped it to data provided from TfL to map the relationship between temperature per degree increment to the frequency of delays in a day. And you can see that there is some variability by whether it's above ground or below ground or at a depot where the trains are stored once the service is finished. So overall, typically you have more delays take place underground than you have above ground, with the exception of when the temperature, the max daily temperature, reaches approximately 24, 25 degrees, where that trend increases. So what you can see is that the relationship of in the environment to the delays are variable in both of the parts of the network, and both need to be looked at independently of each other. So the data I'm using now is a larger database covering a few more years. I've got data from 2006 to current day. So the data I'm using is from St James's Park, one of the central London Met Office weather stations, with surface meteorological data, which I think is hourly, with attributes such as temperature, humidity and precipitation. And I'm combining this data with data log temperature from each platform that's underground across the network provided by TfL, including asset fault data, which is I'm not discussing specifically in this presentation, but is part of the wider PhD project. And this is variable due to historic reasons for the collection of the data. And then this will also be including Viola data, which is a company contracted by TfL that also collect additional meteorological data on site at all the 13 depots across the network. So I'm looking at, can we predict tunnel temperatures? So while I was at the Railway Research Institute, found a Japanese paper that thankfully they were able to translate for me, which was a simple model that uses air temperature data to predict the tunnel temperature. And you can combine a number of variables, which are shown here in the graph, such as the tunnel, so the smaller wave is the tunnel temperature and the wider wave is air temperature. And this is approximately over 2 years, taking that data of daily average temperature, annual average temperature, and the time delay, so the lag in temperature trend, including a ratio of difference between the variance of the two data sets to formulate a model for each area to predict the tunnel temperature. And what I've done is try to apply this model to London Underground data, which is the first time this has been done, to see if this model is, one, viable to use, and two, can be used to add additional climate projection data to. So I'm presenting here to you a sample of the data that I have tested. So I've selected the Oxford Circus station, which is quite central to the central line in the middle of the tunnel. It's quite a hot station. It's a very busy line, so I thought it would be a good one to show to you here. As you can see on the left, this graph here shows the average temperature over year from 2017 to 18 per day. You've got the tunnel temperature of the two tunnels, eastbound and westbound, in the green and the yellow at the top. And you can see that the blue line at the bottom is the above ground temperature at St. James's Park, and that there is a very large disparity between the tunnel and outside temperature, and the variance throughout the year is also far smaller. Nonetheless, the trend is overall the same, so we can infer that there is some relationship of the outside temperature influencing on the inside. Similarly, on the right, we have the daily trend, so the same database and the same data to show the temperature throughout the day. Similarly, there's a lag. There's the highest temperature is around about 7 p.m., 8 p.m. So you can see that there is a build-up of temperature, and I would infer that during the summer you have less time for that temperature to cool down in the evening, and that is building up, and that is leading to an autumnal peak or a lag, an increase in temperature during the autumn period. Okay. What I have done is try to take these variables and model the temperature data for above ground, and I've mapped it here on the central line, Oxford Circus eastbound tunnel. The measurement is the dark blue, so that's the data from the data loggers at the platform. Mapped it according to the calculation in the lighter blue for 2017, 2018. So this is a daily average. And you can see that the model seems to fit quite well, especially during the springtime into the summer. You can see that the calculation does slightly underrepresent the autumnal peak, the lag over time. So there are some externalities I would believe to consider as part of my ongoing research. But nonetheless, looking at this across the other stations, it all seems to fit pretty well. So then what I've done is taken every single observation and mapped it across how well it fits by per degree increment. As you can see, 74% of the data fits the model plus minus 2 degrees for all the observations. And we have also done this with the Bakerloo line, and it sits around the similar. I've still got the other lines to do. So the implications here are I can use this framework to compare the relationships. I can look at the data gaps and fill with that. And we could probably include UKCP 18 parameters using data from when that comes in. And it will help highlight intervention measures effectiveness with if there's, for instance, air conditioning input, you can see hopefully that there will be a drop in the measurements relative to the model. So yeah, to summarise that, we are aware that the London Underground tunnel temperatures are increasing. I'm still working on the impacts of the assets in greater detail. We're also aware that the tunnel and surface network characteristics differ, so we can see that it needs that separate analysis. And the complexity of those tunnel environments will benefit from using this model for future climate projection applications. Yeah, so thank you very much for your attention.
I didn't realise it was quite so hot in the tunnels. That's quite shocking, actually. So we've got a question from Tom. He's saying,
yeah,
a lot of lines are updating to have air-conditioned trains. Do you know anything about how these expel warm air? I.e., if this is expelled in tunnels, will this negate your observations?
This has been discussed that it is likely that air conditioning, yes, it does expel warm air, and as a result would then be probably absorbed by the clay walls as a consequence. The current air-conditioned trains are on the cut and cover tunnels. They're not in any of the deep tube networks, so we're yet to see if that's had an impact. As it stands, there is a limited relationship with, or I've not looked in a great amount of detail on the impacts of the air-conditioned trains themselves on the impacts of those cut and cover lines, but this is particularly looking at the deep tube network, which is slightly different. This research might be able to inform them on some of their engineering standards for their trains. Thank you for your question. It's a great one.
Great answer as well. So Daniel's got a question. Oh no, so Hannah first actually. Have you considered using model analysis or another truth valuable or variable, rather than observations in London, which can be patchy? Another one.
So yeah, this is a great question. This is to be ongoing considered. I have not yet got to that stage. So at the moment, as it stands, I've collected the observation data. The data provided by TfL is well calibrated and quite complete, which has been great. But I would absolutely be considering using models in future. So thank you for that. It'll definitely be ongoing.
Weather forecast to predict dangerously hot conditions on trains to warn people, particularly during summer heat waves.
That's a great aspirational goal. Yeah, I would say so. So the next stage of my research is, once I've got this model in place, is to start looking at not so much the aggregated data for longer periods, but to look at specific heat events and see what happens and see how that applies to the models later down the line. So that would be something that would be great to inform TfL in the future. Absolutely.
That was a really interesting presentation. I think that's the end of the session. So thank you to Sarah and to the rest of the presenters. It's been a really interesting session. So after this, we have the refreshment break, and I think that technically starts at 11. So we've got from now until 11:30 until we have the next poster session. If you haven't already, the photography session will take place in the refreshment session. So do have a look at those photographs and vote for your favourite. Thank you, everyone.